Welcome to Mythos AI, your source for Cliff's Notes on complex subjects. Join Anna and Phil for yet another engaging conversation.
The 2025 Nobel Prize in Physics went to three scientists, recognizing work that, well, it fundamentally shifted how we approach quantum mechanics. For a long time, quantum effects felt like this weird, untouchable thing happening only at the tiniest scales, something you observe, not something you build. Today, we're diving deep into the research that turned those bizarre quantum rules into actual engineering tools.
Yeah.
If you're looking for the origin story of today's quantum processors, this is really it.
That's absolutely right. What John Clarke, Michel Devoret, and John Martinis essentially did was prove you could build an electrical circuit, something macroscopic, something you can, actually fabricate that behaves like an atom.
An artificial atom.
Exactly, an artificial atom. And they showed experimentally that two really core quantum phenomena, macroscopic quantum tunneling and energy quantization, could happen in these circuits. They could be controlled.
And that's the huge leap, isn't it? Taking quantum mechanics from just describing nature to actually using it prescriptively, like here's a recipe to build something quantum.
Precisely. Their experiments laid down the fundamental blueprint for what we now call superconducting qubits. And that platform, well, it's the basis for a lot of current quantum computing efforts and some incredibly sensitive quantum sensors already out there.
Okay, let's unpack that a bit.
Yeah.
A physical circuit showing quantum effects.
Yeah.
I mean, how did they even achieve that? Let's start with tunneling. It sounds like something out of science fiction.
It does, doesn't it? Tunneling is really where classical physics just breaks down. The classic analogy helps here. Imagine a marble in a valley.
Okay.
Classically, if there's a hill, the marble needs enough energy, enough of a push to roll up and over that hill to get to the next valley.
Makes sense.
Quantum tunneling says sometimes the marble can just appear on the other side, as if it went through the hill, through that energy barrier, without ever having the energy to go over it.
Right, passing through something solid, essentially.
Yeah.
So in their experiment back in the mid-'80s at Berkeley, what was the marble and what was the hill?
So the marble wasn't just one particle. That's the macroscopic part. It was the combined quantum state of billions of paired electrons, these things called Cooper pairs, acting in concert, like one single quantum object within a superconducting loop.
Billions of electrons acting as one.
Wow.
Yeah.
And the hill was an energy barrier inherent in the circuit design. Classically, it should have been completely impossible for the circuit's voltage state to switch without adding external energy. It should have been trapped.
But they saw it switch. The voltage just appeared spontaneously.
They did. They saw the system jump across that barrier. But how did they know it was quantum tunneling and not just, say, some random thermal jiggle giving an electron enough energy to hop over?
Yeah, how do you rule that out?
That was the crucial part. They very carefully measured the rate at which this spontaneous switching, this escape, happened. Then they cooled the circuit down, way down, colder than outer space. And as it got colder, the escape rate didn't go to zero, which you'd expect if heat was the cause. Instead, it flattened out. It became constant, totally independent of temperature.
Ah, so it didn't matter how cold it got. The tunneling still happened at the same rate.
Exactly. That temperature independence was the smoking gun. It proved they were seeing a purely quantum phenomenon, macroscopic quantum tunneling, just like the theory predicted.
Okay, that's tunneling where the system can go. But the other big discovery was energy quantization. That's about the states it can actually be in, right?
Right. Think of a ladder. You can stand on this rung or the next rung up, but you can't hover in the space between the rungs.
Got it. Discrete levels.
Exactly. Their circuit behaved just like that. It could only hold specific discrete amounts of energy, like the rungs on the ladder. It wasn't just a wire. It was effectively an artificial atom with its own unique energy levels that they could, well, interact with.
And they proved this how? By shining light on it, metaphorically speaking.
Pretty much. They used microwaves. They beamed microwaves at the circuit and watched carefully. What they saw was that the circuit only absorbed energy at very specific microwave frequencies.
Resonances.
Precisely. And those resonant frequencies perfectly matched the energy differences between the calculated rungs or energy levels of their artificial atom. It confirmed the quantum nature, the quantized energy states.
And the key piece of hardware for this was the Josephson junction.
Yes, absolutely essential. A Josephson junction is basically a sandwich, two superconductors with a very, very thin insulating layer in between. That structure provides what's called nonlinearity or anharmonicity.
And harmonicity,
Yeah.
meaning the energy levels aren't perfectly evenly spaced like a simple pendulum.
Exactly. That uneven spacing, especially between the grand state, the lowest rung, and the first excited state, the next rung up, is absolutely critical. It lets you clearly distinguish the zero state from the one state. Without that anharmonicity from the junction, you wouldn't have a usable qubit.
That physics is incredible. But, okay, you got this artificial atom. But you mentioned the early versions were incredibly fragile. Nanosecond coherence times. That sounds, well, almost useless for computation.
It was a massive challenge. The potential was obviously there, this glimpse of controllable quantum mechanics. But yes, those early qubits were extremely fragile. They'd lose their quantum state, decohere, in billionths of a second, just way too sensitive to environmental noise, especially elliptical charge fluctuations.
So, what turned it around? Was there a specific aha moment?
There was a pivotal engineering insight, yeah.
Yeah.
It came later, around 2007, from Michel Devoret's group again. They developed what's called the transmon qubit.
The transmon. That's the design used everywhere now, right? What did they change?
It sounds almost deceptively simple. They added a large capacitor in parallel with the Josephson junction.
Just adding a capacitor.
Well, it represented a really clever engineering trade-off. By adding that large capacitance, they made the qubit much less sensitive to background charge noise, the very thing that was killing coherence.
Okay, so less sensitive.
Yeah.
But did that hurt its performance in other ways?
It did, slightly. It made the qubit a little less anharmonic, meaning the energy levels were a bit closer together, and it reduced its tunability somewhat. But the gain in noise immunity was huge, exponentially better.
And that trade-off was worth it.
Oh, absolutely. It increased coherence times by orders of magnitude. Suddenly you're talking tens, even hundreds of microseconds instead of nanoseconds. That improvement, that robustness, was what really transformed superconducting circuits from a cool physics experiment into a viable, scalable platform for quantum computing. It's why companies like IBM, Google, Rigetti, they all build on that fundamental transmon design today.
It's amazing how often progress comes down to those clever engineering compromises. Now, quantum computing gets the headlines, but you mentioned sensors too. Did this same foundational work lead to technologies we're using right now?
Yes, absolutely. And this is often overlooked. The same basic physics, the same superconducting circuits with Josephson junctions are the heart of devices called SQUIDs.
SQUIDs, what does that stand for?
Superconducting quantum interference device. And they are, quite simply, the most sensitive detectors of magnetic fields that exist.
How sensitive are we talking?
We're talking about detecting magnetic fields trillions of times weaker than the Earth's own magnetic field. Just incredibly sensitive.
Wow, trillions. So what do you do with that kind of sensitivity?
Well, it has immediate practical applications right now. In hospitals, SQUIDs are used in a technique called magnetoencephalography, or MEG.
Brain scanning.
Essentially, yes. Mapping the tiny magnetic fields produced by brain activity non-invasively. It's used to pinpoint the source of things like epileptic seizures with remarkable precision.
Okay, that's incredible. What else?
Geologists use them. SQUID systems are deployed for high-resolution geological surveys. They can help find deep mineral deposits or map out underground structures for energy exploration.
Finding resources underground.
Exactly. And there's defense applications, too, developing SQUID-based systems for magnetic anomaly detection, or AMAD. Basically, looking for the faint magnetic signatures of submerged objects, like submarines.
So medicine, geology, defense. That's a pretty direct impact from fundamental physics research.
It really is. And actually, there's another key use inside quantum computers themselves. Variations of these circuits form what are called Josephson parametric amplifiers, or JPAs.
Amplifiers for the qubit signals.
Precisely. The signals coming out of qubits when you measure them are incredibly faint. JPAs amplify those signals enough for us to read them, but crucially, they do it while adding the absolute minimum amount of noise allowed by the laws of quantum mechanics. They let us listen in without yelling, essentially.
That's a powerful connection back to the core technology.
Yeah.
So fast forward from those first tunneling experiments 40 years ago. Where are we today with superconducting quantum computing? What's the state of the art?
We're firmly in what people call the NISQ era. NISQ.
NISQ. Noisy Intermediate Scale Quantum.
That's the one. It means we can now build chips with a respectable number of qubits, intermediate scale, say hundreds, like IBM's Osprey or Condor systems pushing towards 1,000. But the N is important. They're still noisy.
Meaning errors are common.
Yes. Individual operations, the quantum gates, still have small error rates. And over the course of a complex calculation, those errors add up and scramble the result. So the computations we can do reliably are limited in depth and complexity. It's like having an early classical computer that was powerful for its time but crashed frequently.
So the big challenge has shifted from just making qubits to making them work reliably together.
Exactly. Making them robust was step one, thanks to things like the transbond. Now, the focus is on system-level reliability and error correction.
And have we made progress there?
Yes, actually, quite significantly, just in the last year or so, late 2024 into 2025, there have been key demonstrations showing that you can reduce the error rate of a logical qubit.
The logical qubit. That's where you use multiple physical qubits to encode information more reliably.
That's right. You use redundancy and active feedback to protect the quantum information from noise, proving that this error correction actually works, that the logical qubit is better than the underlying physical ones. That was a huge milestone. It shows the path towards fault-tolerant machines is real.
Okay, so looking forward then, what should we realistically expect to see in, say, the next couple of years? By late 2027, perhaps?
I think the focus will be twofold: scaling with quality and hitting key error correction milestones. We'll definitely see processors with over 1,000 high-quality physical qubits becoming more common, maybe even standard for leading groups.
More qubits, better quality.
Right. And critically, the community really expects to reach what's called the break-even point for error correction. That's the point where a protected logical qubit demonstrably lasts longer and performs better than any of the individual physical qubits it's made from.
So error correction actually starts helping more than it hurts in terms of overhead.
Exactly. That's a major inflection point. When we hit that, it opens the door to running significantly more complex algorithms.
And what would be the practical result of hitting that break-even point?
Well, the hope and the anticipation is that this will enable the first truly credible, peer-reviewed demonstrations of quantum advantage for a scientific problem. Something like simulating a complex molecule for drug discovery or materials science in a way that's provably beyond the reach of even the biggest classical supercomputers today.
The first real killer app, maybe.
Potentially, yes. For science, at least.
And if we look further out, say 5 to 10 years, towards 2035, what's the trajectory for scaling these systems up to tens of thousands of qubits?
Scaling to that level, well, it almost certainly requires modularity. You probably can't build a single monolithic chip with, say, 50,000 high-quality qubits and all the wiring and control needed. It just becomes an engineering nightmare.
So like connecting multiple smaller chips together.
Precisely. We'll see modular architectures linking multiple quantum processor units, QPUs, together, probably using quantum communication links. Think of it like building a classical supercomputer data center by networking many individual server racks. IBM, for instance, has explicitly stated a goal of reaching a 2,000 logical qubit system by 2033 using this kind of modular approach.
So the future isn't necessarily quantum computers replacing classical ones, but working with them.
Oh, absolutely. That seems to be the consensus. The dominant model going forward will almost certainly be hybrid quantum classical computing. The QPUs won't be standalone machines for most tasks. They'll act as specialized accelerators, tackling the specific parts of a problem like complex simulations or optimization that are intractable classically, while the classical supercomputer handles everything else.
Integrated systems. And just the effort of building these things, that's creating other technological benefits too, right? Spillovers?
Huge spillovers, yes. Just the sheer difficulty of controlling thousands of qubits at near absolute zero temperatures, it's forcing massive innovation. For example, in cryo-CMOS.
Making standard computer chips work in extreme cold.
Exactly. Developing complex control and readout chips based on standard silicon CMOS technology, but making them operate reliably at 4 Kelvin or even colder. That has immediate applications beyond quantum, like for next-generation space telescopes, sensitive radio astronomy detectors, anywhere you need complex electronics in ultra-cold environments.
What else?
Advanced RF engineering, the techniques developed for precisely controlling qubits with microwave pulses, are pushing the boundaries of radio frequency engineering, which could benefit things like 6G communications or advanced radar systems. And even the theory itself is spilling over. We're seeing quantum-inspired algorithms pop up, algorithms developed based on quantum principles, but designed to run on classical computers, and they're proving surprisingly effective for solving certain optimization problems in logistics, finance, and other fields right now.
It's amazing. We started this conversation talking about a Nobel Prize for fundamental physics, proving quantum mechanics can be engineered. And now we see this whole technological ecosystem emerging from it.
It really is a testament to that initial leap, moving from just observing quantum phenomena to actually building tools based on it. That circuit Clarke, Devoret, and Martinis built wasn't just a discovery, it became an engine for innovation.
So a final thought then. We focused on superconducting circuits because they're, well, the platform recognized by the prize and the current industry leader. But is the race over?
That's the provocative question, isn't it? And the answer is almost certainly no. Superconducting qubits are leading in terms of scale and speed right now, yes. But the field is still very much heterogeneous. You have other promising approaches. Trapped ions boast incredibly high fidelity. Photonics offers potential for room temperature operation and scalability. Neutral atoms are scaling up rapidly in qubit numbers. Each has its own strengths and, frankly, its own daunting challenges.
So different horses in the race.
Exactly. And the big open question is this. Can the engineering improvements for superconducting circuits better materials to reduce defects, clever solutions to the wiring bottleneck as systems get huge? Can those advancements overcome the inherent challenges fast enough? Or will a competing platform, maybe one with different underlying physics, find a more elegant or robust path to a truly large-scale, fault-tolerant quantum computer first? It's still very much an open race.
A race between different flavors of engineering, all built on harnessing quantum weirdness. That is a fascinating place to leave it. Thanks so much for walking us through this.
My pleasure. It's exciting territory.
You can find links to dive deeper into the sources and background material we discussed today in your personal notes. We hope you'll join us for our next deep dive.
Thanks for listening to Mythos AI. Stay tuned for more concise insights. And remember to hit the like button and subscribe for future episodes.